Imagine you're an astronaut out for a drift in deep space. You wind up and throw a rock as hard as you can. Standard physics suggests the rock should continue in a straight line at a constant speed forever. But in an actual, physical universe, that rock will eventually slow down and come to a dead stop. This creates a problem for the law of conservation of energy. If energy cannot be created or destroyed, we have to account for where that rock's kinetic energy actually went. We see the same thing happening to light. This glowing light particle has been traveling since shortly after the Big Bang. As the grid of space around it physically stretches over billions of years, the photon's wavelength is pulled and lengthened, shifting its color toward the red end of the spectrum. By the time it reaches us, it has lost 99.9% of its energy. That energy wasn't transferred to anything else. It simply disappeared from the universe. On a cosmic scale, the law of energy conservation is violated. This mystery originally baffled Albert Einstein as he was finalizing his most famous work. In 1915, Einstein gave a series of lectures at the University of Göttingen to debut his general theory of relativity. While the theory was revolutionary, Einstein was struggling with a specific mathematical flaw. His new equations for gravity couldn't prove that the total energy of a system remained constant. He tried to resolve this using objects called pseudotensors, but they were mathematically inconsistent. Depending on which frame of reference an observer used, the gravitational energy of the universe would simply vanish. David Hilbert, one of the world's leading mathematicians, attempted to find the missing energy equations. He eventually discovered a set of identities that showed energy was conserved, but only in a universe that made positions. Noether realized that the energy crisis wasn't a failure of Einstein's equations, but a sign that physicists didn't understand the origin of conservation laws. To find that origin, Noether looked at the inherent symmetries of space and time, starting with a completely empty universe. In an empty void, one location is the same as any other. If you perform an experiment here and then shift the entire universe to the left, the laws of physics are identical. This is spatial translation symmetry. Noether proved that if the physics are truly independent of location, the math requires a specific quantity to be perfectly balanced so that the results stay the same. That conserved quantity is momentum. We see the same logic with orientation. If you rotate the universe by 90 degrees and the physics don't change, the system possesses rotational symmetry. Because the math must remain identical regardless of the angle, a corresponding value is forced to remain constant, angular momentum. This leads to the most abstract symmetry, time. If the laws of physics are the same today or tomorrow, the universe is symmetric under time translation. Noether showed that for the equations of motion to stay the same across time, there is a mathematical necessity for the total energy of the system to be conserved. In Noether's framework, energy conservation emerges as a mathematical requirement of time symmetry. It only exists because the laws of physics remain constant as time passes. This explains why energy conservation fails on a cosmic scale. Our actual universe does not have time translation symmetry. Because the universe is expanding and that expansion is accelerating, the fabric of space is physically stretching apart. This means an experiment performed today happens in a different environment than one performed billions of years from now. The physical background of the universe is changing. Without that time symmetry, Noether's theorem states that energy no longer has to be conserved. The photon loses its energy because the mathematical mandate that kept it constant has been revoked by the expansion of space. This resolves the paradox of the astronaut's rock. Its kinetic energy bleeds into the expanding void as it comes to rest. Energy conservation feels like an absolute rule on human timescales because the expansion of the universe is negligible over a single day. But over millions of years, Noether's math shows that as the universe stretches, energy is allowed to disappear.